Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over a brand new section which is called the area of the region between two curves. This is in the category of application of integration. So we have three learning objectives to achieve, and we're going to have only two videos. In the first video, I'm going to talk about the first learning objective, which is finding the area of a region between two curves by using the definite integration. And in the second video, I'm going to cover two learning objectives. Uh, so the first one is finding the area of a region between two intersecting curves using the definite integration idea. And in the last one, we're going to define the integration as an accumulation process. And then I'm going to explain, in fact, these two learning objectives on two different examples. Let's get started. All right, let's talk about the area of a region between two curves. As an application of the definite integration, we were talking about the area between a curve and the x-axis, but as you see that now we're talking about the area between two curves. So we're going to sort of like tweak this definition a little bit so that we're going to come up with the area of the pink region. So for this to happen, so we start with two continuous functions on the interval a and b. And as you see that the graphs of f and g are all about the x-axis for the time being. All right, to come up with this area, what I'm going to do next is just to come up with the area between the function f and the x-axis first. We have a formula for that from Calc 1. We know how to come up with that by using the definition of the definite integral. And also, we're going to find the area between the curve G and the x-axis. And the difference of these two areas is the area I'm after. And in fact, the definite integral, integral from a to b f of x dx, is the area between the curve f and the x-axis. Okay, and this integral here, integral from a to b of g of x dx, represent this area. So essentially, the difference of two integrals by using the property of integrals is the integral on the same limits, a and b, but this time we're looking at the difference of these two functions. So in other words, if you want to find the area between two curves, we essentially look at the top minus the bottom curve integrated from, let's say, a to b. All right, so let's add a little bit of rigor to obtain this formula. In fact, I'm going to use the definition of the definite integral, and please pay attention to what I'm going to do next here because I'm going to replicate this idea for the next two sections for sure. So when we were talking about the area concept in Calc 1, what we did is to split this interval AB into subintervals, and those subintervals come with the width delta x, okay? And then we just choose a point, let's say xi, within that interval, okay? And then we determine the height of the rectangle coming with the width delta x. That's our representative rectangle. Well, the height of the rectangle is determined by the difference of the function values because this height here is g of xi, and this larger one, this higher one, the bigger height is f of xi. And the difference is in fact the height of this rectangle here. And we know from precalculus that the area of a rectangle is the height times the width, so that the area of the representative rectangle is going to be f of xi minus g of xi times delta x. But the question is, how many of those rectangles do we have within this region? Well, we split the interval into n subintervals. So for each subinterval, we're going to have one representative rectangle. So in the language of definite integration, it's essentially you're taking the sum on I, starting from 1 going all the way to n. So you're calculating the area. So this whole sum represents the sum of those representative rectangles after we partition the interval a and b. And then obviously the whole goal in Calc 1, remember, is to pass the limiting process. So we're going to let n go to infinity. That means we're going to have teeny tiny subintervals, but infinitely many of those. And we're calculating the representative teeny tiny rectangles over there. So when you take the limit, and if that limit exists, that becomes the total area between two curves, and that limit is represented by this integral. Okay, so every time we're going to apply this limiting process to explain a new application concept. So this is now the area. In the next section, it's going to be volume or surface area. So please try to understand this whole logic here, that we always start with a representative rectangle, and then for this purpose of this example, for the purpose of this example, we're talking about the area. So we calculated the area of representative rectangles, took the sum and passed the limit. So then this formula is the formula, in fact, we got right here. All right, here's the good news. So we can extend this formula, in fact, to any two curves and to any area bounded by these two curves on the xy coordinate system. So the area could be below the x-axis or could be crossing the x-axis. It doesn't matter. So the formula is always the same. So as long as you have the vertical lines x equals a and x equals b bounding the region between these two curves, the formula is always the integral from a to b, the top function minus the bottom function dx. All right, let's go for an example. So here's the first example. So find the area of the region bounded by the graphs y equals x squared plus 2, which is a parabola, and y equals negative x, that's a line. And we have two other vertical lines, x equals 0 and x equals 1. So it seems like these four graphs are bounding a region. So now we're going to use the skills from precalculus and Calc 1 to be able to sketch the graphs of those four functions. And if you graph those four functions, and you're going to realize that the parabola, which is f of x equals x squared plus 2, is always about the graph of the line g of x equals negative x here. And as you see that x equals 0, which is the y-axis right here, and x equals 1 is the vertical line here. So as you see that, we're talking about this pink region, the area of the pink region that we're after. So what we're going to do next is to use the formula we have just derived. All right, so let's consider this representative rectangle coming with thickness delta x and height f of x minus g of x. Here we go. And then and what is f of x? That's x squared plus 2, and g of x is negative x. So you simplify that, and you have the integral from 0 to 1, x squared plus 2 minus x dx. And let's just calculate this together. So here we go. This is integral from 0 to 1, x squared plus 2 plus x dx. And we have the power rule for integration. That is x cubed over 3 plus 2x plus x squared over 2 from 0 to 1. And if you substitute the upper limit, so you have 1/3 plus 2 plus 1/2. And then we substitute the lower limit, but the lower limit takes you to 0 all the way, right? Because if you substitute 0 for x, that is going to add up to 0. So then this should be the final answer, which is 17/6. All right, practice time. So please visit the recitation PowerPoint slides and look at the first question. And the first question is asking you to sketch the region. You can use your calculator, but you can also use the skills that we gained in precalculus and Calc 1. I would just in fact, use both of them. So use your skills together with the calculator output and try to sketch the region first and find the area of the region and try to tackle with this problem by yourself. And if you can't find out, please watch the video and see what I will have to do to solve this problem. And the regions are like, looks like this, so please make sure you have that. And in the next question, please pay attention to this question, because here the functions are given in terms of y. So the representative rectangles are not going to be like this, vertical, but they are going to be horizontal, okay? And you will see what I'm talking about when you start checking the video with this. Even before the video, just try to make some sense out of this idea of having a horizontal type representative rectangle, so that the area integral is going to depend on not x but y. So instead of dx, you're going to have, so here you have dx, but instead of that you're going to have dy type integration. And the region looks like this one. So just for your reference, please check this out. And also the next question on the list is sketching the region bounded by the graphs of the equation. So you have a rational function to start with. You have y equals 4, x equals 0, and please watch the video to see what I'm gonna have to do to solve this problem. And here's the region corresponding to this problem. All right, I think that's all it is for the first learning objective, and please move on to my next video after you're done with all the practice problems to see what I'm gonna say for the second learning objective of this section.